All right, today we're going to be detectives. We're diving into an investigation of one of the biggest ideas in all of science. And we're going to use clues that have been hidden for millions of years, written right into the stone of the Earth itself. Okay, let's get into it.
So let's start with our first piece of evidence. Just look at this. It's a 150-million-year-old fossil called Archaeopteryx, and it kind of looks like this bizarre mix of a reptile and a bird. A mysterious clue sent to us from the deep past. So what story is it trying to tell us? Well, to figure that out, we have to ask the right question.
And that really is the heart of it, isn't it? This is the big question for our investigation today. See, we're not just going to talk about evolution as some abstract idea. No, we are going to build the case for it piece by piece using the actual physical evidence that's been left behind.
So here's our game plan for today. We'll start by digging into our main body of evidence, the fossil record. Then we'll analyze some specific clues and see how scientists can build a timeline. After that, we'll connect the dots with some truly game-changing finds, before we finally look at just how fast all this change can happen. Let's begin.
First things first, in any good detective story, you've got to know your evidence, right? So what are we actually looking for when we talk about the fossil record?
You know, at its most basic, a fossil is just any trace of life from the past. It could be something obvious, like a bone or a tooth or a shell, or it could be way more subtle, like a footprint. These are the snapshots, the fundamental clues in our detective story.
And these clues come in all sorts of different forms. Sometimes we get incredibly lucky and find unaltered fossils, like a whole mammoth frozen in ice, or an insect perfectly preserved in amber. But more often, the fossils are altered, meaning minerals have seeped in and replaced the original stuff. And then you've got trace fossils, which are just so cool. They aren't the animal itself, but they're clues about its behavior, how it moved, where it lived. It's like a window into an ancient world.
Okay, so we know what we're looking for. Now let's look at a few high-profile cases. What kind of stories can these ancient clues actually tell us about the lives of these creatures?
Okay, check this out. On one side, you have a woolly mammoth, preserved so perfectly in ice that scientists could actually see what it ate for its last meal. We're talking grass from over 22,000 years ago. And then on the other side, those are the Laetoli footprints. These are incredible. They're not bones, but they are undeniable proof that our early ancestors, Australopithecus afarensis, walked upright on two legs 3.6 million years ago. See? These aren't just rocks, they're stories.
And this story is happening all over the globe. Take Sri Lanka, for example. We find Jurassic plant fossils there that connect it all the way back to the supercontinent Gondwanaland. Marine fossils tell us that parts of the island used to be a shallow sea. And finds from places like the Fa Hien Lena Cave, we're talking bone tools from early modern humans almost 40,000 years ago. It just weaves this local history right into the massive tapestry of human evolution.
Okay, so we've got our clues, we've got our stories. But every good detective needs a timeline, right? How in the world do scientists figure out how old a fossil is? Well, for that, we need to pull out the forensic toolkit.
There are really two main ways to do this. Relative dating is all about logic. It's pretty simple. If you have a stack of undisturbed rock layers, the stuff on the bottom is older than the stuff on top. It tells you the sequence of events. But if you want an actual number, a real age, you need absolute dating. This is where it gets really cool. It works like a tiny geological clock, using the predictable decay of radioactive elements to pinpoint an age in thousands or even millions of years.
Now, what's really clever here is that different clocks are used for different time scales. It all comes down to something called a half-life. That's just the time it takes for half of the radioactive stuff to decay. So for more recent things, say up to about 50,000 years old, carbon-14 is your go-to method. But for the really, really old stuff, dinosaurs, early human ancestors, you need clocks that tick much more slowly, like potassium-argon or uranium-lead. You find those in the volcanic rock layers around the fossils.
Okay, we know what fossils are. We know how to date them. Now we get to the real heart of the investigation, the evidence that literally connects the dots between different kinds of life. This, right here, is the smoking gun.
And that smoking gun is something called a transitional fossil. Now, these aren't missing links like you see in cartoons. Not at all. They are stunningly complete fossils that show a perfect mix of features, some from an older ancestral group and some from the newer descendant group. It is literally evolution caught in the act.
So let's circle back to our very first clue, Archaeopteryx. On one side, you've got the fossil itself. On the other, a reconstruction of what it probably looked like. It is the perfect bridge. You don't have to imagine the link between reptiles and birds. You can see it. It's right there.
And this is what makes it so amazing. Let's break it down. Archaeopteryx had feathers and a wishbone. Classic bird features, right? But it also had a jaw full of teeth, little claws on its wings, and a long, bony tail. Those are all reptilian traits. It's not a reptile, and it's not quite a modern bird. It's both. This is just undeniable proof of that transition from one to the other. And Archaeopteryx isn't some lonely example. The fossil record for horses is just beautiful. It lays out a clear 60-million-year journey. We start with this little dog-sized animal with multiple toes living in the forest, and over time, we see the fossils document this gradual change. They get bigger, the toes fuse into a single hoof, and their teeth change to become perfect for grinding tough grasses on the open plains. It's a perfect story of adaptation.
And we have to talk about another star witness, Tiktaalik. This amazing creature got the nickname fishapod, and for good reason. It had fishy things like scales, gills, and fins. But, get this, inside those fins were the bones of a wrist, an elbow, a shoulder, the beginnings of a limb for walking on land. It could even move its neck independently of its body. Tiktaalik shows us the very moment life was making its move from water to land.
So the evidence for change over time is just overwhelming. But that leads to another question. How fast did it happen? Was it a slow, steady crawl, or was it more like a series of sprints? That's the final piece of our puzzle. So, scientists have a couple of main ideas about the pace of evolution. The first is gradualism. That's the classic idea of slow, steady, continuous change happening over millions of years. But there's another idea called punctuated equilibrium. This suggests that for long stretches of time, species don't change much at all. That's the equilibrium part. And then that stability is punctuated by relatively rapid bursts of big changes. And this diagram really helps visualize the difference. On the left, you see that slow, gradual branching of gradualism. But on the right, you see those long, straight, vertical lines. That's the stability in punctuated equilibrium. And then suddenly a sharp turn, a new branch. And what's fascinating is that the fossil record seems to show both. Some lineages change slowly, while others, maybe when the environment changes quickly, evolve in these rapid bursts. So after looking at all the clues, what's the verdict? Well, the case is pretty clear. Fossils give us the strongest direct evidence for evolution. Those incredible transitional fossils show us exactly how that change happens, connecting the dots between major groups. And our dating methods prove that there has been an immense amount of time for all of this to happen. The evidence isn't just an idea. It's observable, it's testable, and it's solid. And all of this really brings us to one final crucial point. When you hear a scientist use the word theory, like the theory of evolution, they don't mean it's just a guess or a hunch. Not at all. In science, a theory is a powerful, well-supported explanation built on a mountain of evidence. It's a detective story that's been written in stone, just waiting for us to read it.